Hello. Hi, Avishai.
Hey, yes.
Can you hear me?
Yes.
Okay, so I'm now connected through my iPhone again.
Mm.
So I guess that's the way it's going to have to be. All right. It's funny.
Yeah, I don't know what's going on.
Yeah. Okay. I think let's see. So I set you up as co-host. Yeah, you're host as well, right? And I'm okay. And you've set up everybody, the tutors as well as co-hosts. So Avishai, you are the host now, right?
I changed it to you. Actually, once I did it, I'm not co-host anymore. So.
Okay, so let me make sure that you are. Okay, so you're co-host as well.
Okay, good.
Okay, and then I just wanted to make sure that chat is.
Is it open between people? That I?
Yeah, it should be. There should be private chat enabled. Let me just make sure. Okay, now it's enabled.
Okay. Okay.
So private is enabled.
Okay.
Okay, good. Good. I'll just make sure I'm charging my phone.
Anamira, do you want to introduce yourself? Anamira is going to be the moderator of the Tuesday lectures.
Okay, great.
Hello, I'm Anamira. It is now recording. That was also one of my responsibilities. Yes, I'm here. I'm a tutor. I'm here to moderate and mute people and unmute people.
Great. Welcome, Anamira.
Thank you.
Okay, so a couple of minutes to go.
Professors, if I need to get your attention, is it better that I message you directly through the chat, or if I just interrupt you and read out the question from the chat, if there's a good question?
It's better to unmute yourself because we will probably not be reading the chat.
Okay.
And you know, one way you could do this is if it's an urgent question, then do go ahead and unmute. And otherwise, I'm going to stop every 15 minutes or so and ask for questions. So you know, if there's something that's a clarifying question, which is better asked immediately, then please do so. And yeah.
Okay, sounds good. I'll try to use my gut for the timing.
Right. Great. Now, there's one other thing here, which is I think it always highlights my iPhone, the thing that I'm calling on rather than the video, but not sure there's anything to be done about that. Is there a setting?
Yes, if the host, there's like an ellipsis at the top right for each video. If you do spotlight video, then that should spotlight it on the recording as long as it's enabled.
Sorry, it's on the top right?
Top right, yes, I believe so.
And then what do I do there?
Do you see an option that's like spotlight video or something?
I changed it to spotlight, so I think it should work.
Okay. 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 Great. Excellent. Okay, so let's see. We just.
No, but the thing is that in January, nothing. guess they went to their supplier and they said, I want $500,000 of vouchers, but
It's
they
okay.
Professor, I think someone muted your phone when they hit mute all.
Yeah, Umesh, can you unmute yourself? I needed to unmute everybody. So.
Okay. And let me just share my screen. Okay, so okay, so let's see, welcome everybody. And okay, so today we're going to talk about the fast Fourier transform. So, you know, the fast Fourier transform is one of the great algorithms. So, you know, Gilbert Strang, who wrote the book on linear algebra, called it the greatest numerical algorithm of our lifetimes. So it's also probably the canonical divide and conquer algorithm. The other thing I'm told about this algorithm is that students in 170, you know, look back on it very fondly as something that they, you know, they really think of it as something really very interesting and one of the, you know, most interesting algorithms that they've seen. That's how they look back on it. When they're doing it, many actually find it very difficult. Okay, so, you know, I'll view as my challenge today to try to make it really accessible to you. So let's try to, you know, so I'm going to do my best, and, you know, you should try to do your best to, you know, focus and see if we can actually make this into, you know, into the kind of, you know, joy that in the moment that that people experience afterwards, you know, after when they are thinking back about it. Okay, so what's the FFT? You know, it's an algorithm that you know, I'd mentioned in the first lecture. It gives a way of multiplying polynomials very fast, right? So it gives a way of taking two polynomials, a0 plus a1x plus dot an minus 1 x to the n minus 1. If you want to multiply this times b0 plus b1x plus b n minus 1 x to the n minus 1. Now, if you were just multiplying these two polynomials out, the obvious way to do it is to write this as summation over I and j going from 0 to n minus 1 of ai bj x to the power of I plus j. And you can see clearly this takes n squared time because you have to do n squared multiplications, because I is, you know, I is running through n things and j is running through n things. Okay, so basically the FFT, the fast Fourier transform, takes this from, you know, it takes this algorithm which was order n squared, and FFT is order n log n. Okay. Now this algorithm, the FFT algorithm, has many important applications. So I'll just list out a few of them. One of them is that it gives us a very fast algorithm for integer multiplication. So basically, you can do integer multiplication which we saw with Karatsuba's algorithm was roughly n to the 1.7. Now it reduces it to essentially order n log n. There might be a log n thrown in. So, you know, that's one sense in which you could say this is the ultimate divide and conquer algorithm. Second thing you can do with it is what I just spoke about, polynomial multiplication. And polynomial multiplication is sort of very fundamental to all kinds of digital signal processing. It's used in filtering, it's used in MPEG compression, JPEG compression. And actually the most general thing, you know, you can think about is something if you've probably seen if you did linear time invariant systems. So basically when you're doing linear time invariant systems, you're given some box, you know, like an amplifier or some other kind of electronics box where you're feeding in a signal and it's converting it into an output signal. Now, the signal that you're feeding in is some function of time. So there's time and there's the signal, right? And one way you can process the signal, you know, in digital signal processing, what you do is you discretize the signal. So you just sample the signal every so often. And then you can call the value at time t a sub t, right? And so your signal now becomes a naught, a1, a sub n minus 1. If you're going for t equal to 0 to n minus 1. Okay. And now we have an, you know, so we want to understand, given that this box is linear and time invariant, what does the output look like? So it turns out if this is a linear time invariant box, so if it's linear time invariant, then it's characterized by what happens if you kick it at time 0. So in other words, if you give it a unit input at time t equal to 0, and you look at what the output is, the output of the box, then let's say the output of the box is B0, B1, B2, ... B n minus 1. So the output of the box is also some signal that varies with time. And if you discretize it, it looks like B0, B1, etc., B sub t. And now what, okay, so this is the thing we know about the box. We know that the box, if we kick it at time t equal to 0, it outputs B0, B1, B2 up to Bn minus 1. Now, what we are told is that it's linear and time invariant, which means linear means if we feed in 2 signals, then the output is going to be the sum of the 2 outputs we'd get if we just fed in the first signal or if we just fed in the second signal. Okay? And that's linear, it's time invariant means that if instead of kicking it at time t equal to 0, if we kick it at time t equal to 1, then we'll see the same output, except it's going to be delayed by 1 time unit. Okay? So here's how we're going to think about it. We are going to think about the output on a unit, you know, on an input of 1 at time t equal to 0. As B0 plus B1t plus B2 t squared plus Bn minus 1 t to the n minus 1. where now we are thinking of t as a unit time period. Okay, or it's if the use of t is confusing here, let me write a different variable just to indicate that this is a different variable. So let me just call it b0 plus b1x plus bn minus 1 x to the n minus 1. So x represents one time unit, a delay by one time unit. X to the x squared represents a delay by 2 time units, and so on. So now if instead of giving a unit input at time t equal to 0, we give an input of a0 at time t equal to 0, then our output is going to be what? Well, you know, output is going to, it's linear, so it's just going to scale with a0. So the output is going to be a0 times b0 plus b1x plus dot 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 bn minus 1 x to the n minus 1. What if we give an input of a1 at time t equal to 1? Well, remember what happens is if you shift the input by 1, the output is going to shift by 1, but it's still going to be the same output. So the way to denote it is the output will be a1 times t times b0 plus b1x. Oops. Remember, I switched from t to x. a1 times x times b0 plus b1x plus dot 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 bn minus 1 x to the n minus 1. And so now if we just generalize, then if the input is a0 plus a1x plus an minus 1 x to the n minus 1, right? Meaning we have an input of a0 at time equal to 0, a1 at time t equal to 1, and so on. Then the output is going to be a0 times this polynomial plus a1x times the same polynomial plus a2x squared times the same polynomial dot dot dot, right? And as you can see, this is just a of x times b of x. Right? Does this make sense? Okay, so you know, this algorithm had a completely revolutionary effect on digital signal processing. In fact, one could say it made digital signal processing possible. It's also something that's used in astronomy, in interferometry, in you know, in these large, when you have big data in astronomy, like in the LIGO project, then it's processed using fast Fourier transform. It's also used in MRI machines, you know, in order to, you know, collect the signals and then make sense of them. In fact, the way the FFT was invented, this was in 1963. There was President Kennedy had his science council, and at that, you know, at one of these science councils, the challenge was, how do you process, you know, nuclear test data? So they wanted to process nuclear test data from the Soviet Union using different probes, you know, that they had in different, you know, in different parts of Europe. And they wanted to take this data they got from different parts of Europe and use them to detect nuclear tests and analyze them, tests that the Soviet Union had been doing. And in order to do these tests, you had to compute Fourier transforms very fast. And so Tukey, who was a mathematician from Princeton, was at the meeting, and he suggested that one could do this using this algorithm. You know, he sort of sketched out the algorithm. And you know, at the same time, there was somebody from from IBM who was there, who went back to IBM and asked one of the people on his team, Cooley, to program it up. And so after they programmed it up, they realized, it was going to be extremely useful. So, Cooley reached out to Tukey and said, well, let's write up a paper together. And Tukey sort of said, well, no, this is really well known. I just sketched out to you known ideas. But eventually, Cooley convinced him, and they wrote up the paper. And it's one of the most cited papers, one of the most famous papers in algorithms. Now, it turns out that what Tukey said about the algorithm was actually true, because he thought of it as something that was sort of it was folklore. And in fact, Gauss, the same Gauss who was responsible for this this trick that we used in Karatsuba's algorithm, the same Gauss who came up with that trick when he was in grade school, actually also came up with essentially the fast Fourier transform algorithm back in 1805. And he came up with it in the context of analyzing the orbits of asteroids, two asteroids that he was interested in, Pallas and Jonas. And so basically he used, he sketched out essentially the same algorithm in that context. Okay, so maybe let me stop here for a couple of minutes for questions, and before we proceed further.
I think we have some signal processing specific questions.
Okay.
One from Kentaro. He raised his hand in Zoom.
Do you want?
So why do we take each x to a power of like n-1, for example, for the last one? And why do we take it to some power instead of just keeping it like a simple linear combination?
Oh, what do we mean by, so I'm just saying, look, we want some way of saying that the input b sub 2 was delayed by 2 steps. So to keep track of it, we put in a variable x and raise it to the power of 2 to say it was delayed by 2, right? And then if we want to say, what was the effect on the output? Well, we say, look, if it happened, so if it happened that, so let's write down a of x. A of x is what the output would have been if the input had been at time 0. But now we had an input of a2 at time 2. So the entire thing is going to be delayed by 2 units. And by writing each of these coefficients down with a power of x, anytime we delay the input, we are multiplying by, so here we are multiplying by x squared to say the input was delayed by 2. And in fact, every, sorry, this would have been b of x, right? So does that make sense? That so in other words, suppose the output was 3 plus 5x plus 2x squared. What does 3 plus 5x plus 2x squared mean? It means that at time 0, the output is 3. At time 1, the output is 5. And at 2, the output is 2. Right? That's what the output looks like. Right? This. Right? Now suppose that instead the input was delayed, right? So the input was actually 2 at time 2. Say it was 2 at time 1. So now we'd multiply this by 2x, and so the polynomial we'll get is 6x plus 10x squared plus 4x cubed. Okay, which means, so this says at time t equal to 1, the output is 6. At time t equal to 2, the output is 10. And at time t equal to 3, the output is 4. Okay, so this is just a way of representing what we want the input output to be, right?
Oh, so the exponents are just like times. So it's like when we multiply by 2x, we're shifting by 1 because the exponent is 1, and then we're amplifying by 2.
Yeah.
Okay.
Yeah, that's because the input was of magnitude 2, not of 1.
Okay. And what does x represent? Or is it just like what
It
does
just represents 1 unit of time here. Right? Right?
all right, thank you.
Okay.
There might be a few more questions. So we should pause for a couple more seconds.
Hi, I have a question, Professor.
Yes.
So like this is my first time learning about this, so it might be a stupid question, but so if we get a signal, to get the output signal, we have to multiply by this polynomial that we set up, which is b0 plus b1x plus all the way to b sub n minus 1 times x to the n minus 1 power.
Mhm.
So is that just a rule we have? So we just made up that polynomial, right? To process the signal.
Right. So basically, you know, if we are studying linear time invariant systems, then you know, the system, and there are a lot of systems that are studied that are linear time invariant. It's a big field. So now these systems are characterized by how they respond if you just hit them, right? So with an impulse response. So you just give it an input, a very sharp input at one moment in time, and you see what kind of output it produces over time. Okay.
Okay.
So that output is represented by this polynomial b. Okay. So here, let me write this out. So the impulse response is b of x, right? So this polynomial tells us, you know, if you just hit it, then, you know, how does it ring over time? You know, what you know, its output is b0 and b1, then, you know, so over time it gives you that output. So now instead of having the input be an impulse, now the input is a of x. So now your input is not just for one moment, but it's a signal which takes some time. And now we want to understand what's the output. And the answer is the output is going to be a of x times b of x. So you multiply the two polynomials out.
Okay, so basically we set up b of x to like find the impulse responses from a of x and then produce it into a polynomial.
So b of x is the only thing you need to know about the system to understand how it responds to any input. Okay. Now you're given an arbitrary input. So you write out the input as a of x, and now your output is going to be a of x times b of x.
Okay.
Okay.
Thank you, Professor.
You're welcome.
It looks like Kentaro's hand is still raised. Kentaro, do you still have a question?
Yeah, so just to clarify, we're just, so the input, the impulse that we're applying is v of x, so that's why we multiply at each time, because it's like whatever we have at time equals 0 is what it's based on, and then we're just applying impulses like throughout the time.
Exactly. So any input a of x, you know, any arbitrary input is a sequence of impulses at time 0, 1, 2, etc., etc.
Oh.
And so now you break it up into impulses at time 0, 1, 2. You know, for each such input, which is an impulse, you'll get an output. What's your output going to look like? Well, it's going to look like b of x, except it's going to be delayed by exactly how much your input was delayed, and it's going to be magnified by exactly how much your input value was.
Yeah.
Right. Okay. So you take b of x, you magnify it by the appropriate constant, you delay it by the appropriate amount of time, and that's your response to the impulse at that moment. Now, since it's a linear system, you can add together all these outputs. So you have your sequence of impulses, each of which gives you an output. Your combined output is going to be the sum of all of these. So you go ahead and add all of these pieces together, and that's exactly by definition equal to A of x times B of x.
Oh, okay. Thank you.
Okay. All right. So let's move on. And let's now, let's now talk about notation and representation, right? So there are many ways we can represent a polynomial. So we have a polynomial a0 plus a1x plus dot 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 plus an minus 1 x to the n minus 1. Here's another way you can write it out. You could write it out in this notation as a vector, an n-dimensional vector, a0, a1, a n minus 1, right? It's all in the, it's all in how you look at it, right? It's in your mind. A polynomial is just given by its sequence of coefficients. So this we can call the coefficient representation. That's how we can write out what this polynomial is. Now, there's one other thing we can do with this polynomial. What we could do is we could pick a point x0 and evaluate the polynomial at x0. So we could pick a particular point x0, say x0 equal to 0, and say what's the value of this polynomial a. So let me call this a of x. Right? What's the value of a of x at the point x equal to x0? So we could write out a of x0. And similarly, we could evaluate it at x1 and call that a of x1. And so we could pick several distinct points at which to evaluate this polynomial. And maybe we could pick n different points. Okay, so pick n distinct points, x0, x1 through xn minus 1. N different points, or n different numbers, x0 through xn minus 1. And we could evaluate the polynomial a at these points. Right? And for example, if you were to compute a of minus 1, this would just be a0 minus a1 plus a2 minus a3 dot dot dot. Right? Now again, we can write this out, in also as a vector. A of x0, a of x1, a of xn minus 1. Okay. Now, there's something that you learned in CS170, something really simple but very important about polynomials, which is if I give you the value of a polynomial of degree n minus 1 at n minus 1, sorry, of degree n minus 1 at n distinct points, then that uniquely specifies what the polynomial is, right? So there's a way to, if I give you the coefficients, I can figure out the values of the polynomial at these n different points. But if I give you the values of the n different points, then we can also figure out what the polynomial was. So there's a one-to-one correspondence between the two, right? So this is called the value representation. And of course, it depends upon which endpoints you choose, right? But once you fix the endpoints that you choose, x0 through xn minus 1, then you can write the polynomial either in the coefficient representation or in the value representation, and you can go back and forth, right? It might take time to go back and forth, but if you manage to go back and forth, these are equivalent representations. Okay, so now let's do a little bit more of notation. So I could write a vector like this, 1x, x squared, x to the n minus 1. I could write a row vector like this and multiply it by a column vector, A naught, A1, AN minus 1. And this evaluates to A of x, right? Does that make sense? So for example, if I wanted to compute A of minus 1, I could say A of minus 1 is just, I'd write out the row vector 1. If x is 1, so this would be minus 1, x squared would be 1, x cubed would be minus 1, dot, 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 times A naught, A1, AN minus 1. Right? It would just be A naught minus A1 plus A2, etc. Okay, so that's another way to write out how you evaluate the polynomial at a point x. So now, if you want to evaluate the polynomial at points x0, x1 through xn minus 1, how do we do it? Well, clearly, what we should do is write out a matrix whose first row is 1, x0, x0 squared, x0 squared, dot, 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 x0 to the n minus 1, 1, x1, x1 squared, x1 to the n minus 1, 1, xn minus 1, xn minus 1 squared, xn minus 1 to the n minus 1, and then multiply by A naught, an minus 1. And what we'll get is the values at each of these points. A of x naught, A of x1, A of xn minus 1. Okay. So when I said the fast Fourier transform is an algorithm to multiply polynomials, I was sort of getting ahead of myself. What the fast Fourier transform is a way of moving from this representation to that representation. So given the coefficients of the polynomial, it creates the values of the polynomial at endpoints. Okay, so the FFT, it goes from coefficient representation to the value representation. So you're given as input the polynomial A in the coefficient representation, and it gives back to you the value representation. Okay, so now on the face of it, this didn't help us very much because to compute each of these, the value at each of these points, you have to do n operations, and you have to compute n values, so it's n squared time. So actually the FFT, remember I said the value representation depends, you have to fix your n distinct points, x0 through xn minus 1. So what it does is it goes from the coefficient representation to the value representation for a clever choice of x0 through xn minus 1. So for the value representation, we get to fix x0, x1 through xn minus 1. And so we choose x0 through xn minus 1 very cleverly so that we can compute all these n different values very quickly. Okay, is this clear? Maybe I'll stop for a minute here to see if there are questions. Yeah, everything clear?
It looks like we might need some clarification on what inverse FFT is.
What's an inverse FFT? Okay, I'll get to that in a minute. So you're ahead of me so far. Okay, so let me well, while we are waiting for questions, or in case there are no questions, let me just push ahead just a little bit. So let me just give you an example of special points, where things might be easy. So if we were computing a of 1, this would just be, x equal to 1. So a of 1 is just a naught plus a1 plus a2 plus dot 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 plus a n minus 1. And if you look at a of minus 1, this is a naught minus a1 plus a2 minus a3 dot dot dot. Okay, and so what you can see is that a of 1 and a of minus 1, they have a lot in common. So for example, what they have in common is they look like a naught plus a2 plus a4 plus dot 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 plus or minus a1 plus a3 plus a5 dot dot dot. Okay, so this is what it means to choose these points cleverly. So we're going to choose them cleverly so that when we go to compute the value at different points, it turns out that the computation is almost the same, so that we can share a lot of the computation together. And instead of doing n times as much work to compute the values at n points, we'll only do log n times as much work to compute it at all n points. Okay. Okay, so that's the whole idea behind the FFT. Okay, so now let me, oops. Yeah, oops. Okay. All right, so let's go back and look at our picture. So we have the coefficient representation, and then the value representation for some special points. So the values at x0, x1 through xn minus 1 for some special choice of x0 through xn minus 1. And then the FFT allows you to go from the coefficient representation to the value representation. And the inverse FFT allows you to go from the value representation to the coefficient representation. And the point is that you can go back and forth in order n log n steps. Right? This is what the FFT promises us. Okay, so let's just make sure that this allows us to do polynomial multiplication. Okay. Actually, maybe you should think about whether you can, I just want to make sure that everybody sees that you can use this to do polynomial multiplication. Maybe I'll stop for questions and see if anybody has questions about why this allows one to do polynomial multiplication.
If there aren't any questions, it might be useful to talk a little bit more about why this transformation between the coefficients and the values is useful for the signal processing example. I think that's coming up in the chat.
Okay, that's what's coming up. So remember, in the signal processing example, we wanted to multiply two polynomials. So what we have to show is that if you can do this transformation, then you can multiply polynomials very quickly, right? This allows you to multiply two polynomials of degree n in only order n log n steps. Okay, so actually let's take two polynomials not of degree n, but of degree n over 2. Okay, so let me assume that you're given two polynomials. So I'm going to assume we are given a of x and b of x of degree at most n over 2. Well, n over 2 minus 1, I guess. Right, so they are going to be n over 2 coefficients. And then what I'll do is, you know, I'll just pad it out with zeros so that I'll write a of x, even though it's of degree n over 2 minus 1, I'm just going to write it as a degree n minus 1 polynomial just by making all the higher order coefficients 0. Right? So if I have a polynomial of degree 1, you know, x plus 5, I can always write it as a polynomial of degree 3 by writing plus 0 times x squared plus 0 times x cubed. Right? So there's no problem increasing the degree just by putting in zeros as coefficients. So I'm going to assume that a of x and b of x are both of degree at most n smaller than n over 2. Okay, so then a of x times b of x is of degree less than or equal to n minus 1. Right? It's at most twice as large. So it's certainly smaller than n minus 1. So now what do I do? Well, I can take a of x and write it in its value representation. And similarly, I could take b of x and write b of x in its value representation as well as b of x naught, b of x1, b of xn minus 1. Now, given the value representation for a of x and b of x, how do we compute the value representation of a of x times b of x? Right? If you want to write the value representation of a of x times b of x, what do you have to do? What's its value? What's the value of a of x times b of x at x equal to x naught? Right, it's just a of x naught times b of x naught. Right? What's the value at x1? It's just a of x1 times b of x1. Similarly, a of xn minus 1, b of xn minus 1. So it takes only n multiplications to write out the value representation of a of x times b of x. Sorry, I keep switching between lowercase and uppercase. So let me just state here, a of x equal to a of x, right? I keep slipping up, so let's just say they both refer to the same thing, right? Okay. All right, so it's just referring to the polynomial, either with a capital A or a small a. Okay, so now, I've taken these two polynomials, a of x, b of x. I've computed the product, a of x times b of x, and then I have the values at n minus 1 distinct points. But I also know the degree of this polynomial is at most n minus 1, which means its values at these n minus 1 points uniquely determines the product polynomial. So now if I want the polynomial in its coefficient representation, how would I find it? Well, I just compute FFT inverse, right? And now here I would get the coefficients of the polynomials, C0, C1, Cn minus 1. So I'm assuming that C0 plus C1x plus Cn minus 1 x to the n minus 1 is this polynomial a of x times b of x. Right? And so we managed to figure out the coefficient representation of that polynomial in order n log n steps. Is this clear? Okay, so from now on, for us, the FFT is just switching between the coefficient representation and the value representation for appropriate choice of n points, x0 through xn minus 1. Okay? All right, so now we are going to get into the nitty-gritty of the algorithm. So this is your last chance to stop me before we get into that.
I was wondering, where does the log n come from? Because I can see that there's O of n to multiply n of the numbers.
Now, where does log n come from? You know, it's going to be a divide and conquer algorithm, and then you can guess where log n comes from. It's going to be log n levels of recursion.
Mhm.
And at each level of recursion, we are going to take order n steps. So it's going to look like the recurrence relation for sorting, for merge sort.
Is it because we're splitting it into like half-size arrays like we did? So like n over 2 size, degree n over
So it's going, well, let's look at how it works out. It's really it's a very nice algorithm. It's a very pretty algorithm. Okay, so everyone ready to move on? Okay, so the main question here is which endpoints? And so remember the example we looked at where we said if we evaluate a of 1 and a of -1, there's a lot in common. Well, the kinds of points that we'll choose are going to be the nth roots of unity. Okay, so these 1 and -1 are the square roots of unity. We could look at cube roots, fourth roots, and so on. So we're going to look at the nth roots of unity. Right? So we are going to look at numbers. We're going to look at a number n such that omega to the n equal to 1. Okay? And in general, when you start looking at roots of 1, so you start with what are the square roots of 1? Well, and for everything we're going to do, we'll think of n as a power of 2, right? To simplify things. Okay, so if you look at the square roots of 1, they are 1 and -1. Now, if you look at the square roots of these, well, if you want to look at the fourth roots of 1, the fourth roots of 1 are going to correspond to the 2 square roots of +1 and the 2 square roots of -1, right? The 2 square roots of 1 are 1 and -1. And indeed, if you raise these to the power 4, you get back 1. But the 2 square roots of -1 are I and -I. Right? And then again, if you want the 8th roots of 1, the 2 square roots of these, well, we know they're 1 and -1. The 2 square roots of these, we also know they're I and -I. Right? I is the imaginary number, I squared is -1. But what about the 2 square roots of I? What do those look like? Okay, so if you remember, 1 plus I times 1 plus I is just, you get 1 squared plus I squared plus 2 times I. Remember, I squared is -1, so this is 1 minus 1 plus 2I. So that's just 2 times I. And so if you want the square root of I, you want to divide this by 2. So what you want here is 1 plus I divided by square root of 2. So if 1 plus I divided by square root 2 is one of the square roots of I, what's the other square root? It's just minus 1 plus I divided by square root 2. Okay. And what about the square roots of -I? I think it should be something like 1 minus I divided by square root 2. Right? And minus of that. right? Because 1 minus I times 1 minus I is just 1 squared plus I squared minus 2I. So this is again minus 2I, right? Okay. And then you can keep taking square roots, and this way you'll get the nth roots of unity. Okay. Okay. So it turns out that these nth roots of unity are not, they aren't just, like the fourth roots of unity. They are not just 4 numbers. It's, it's actually the case that if you look at I, if you look at these 4 numbers, so if you want to look at these fourth roots of 1, there are 4 of them, right? There are 1, minus 1, I, minus I. Actually, what you can do is take one of these, these are fourth roots, but they're also, one is sort of the first root of unit, so sort of minus 1 is a square root of unity. So, but I is a genuine fourth root of unity. And it turns out if you take I and you take its powers, you'll get all the fourth roots of unity. So you get I squared, which is minus 1. What's I cubed? So I cubed is I times I squared, which is minus I. And I to the 4th, which is plus 1, right? So when you look at the powers of I, you get all the fourth roots of unity. And so that's true even when you take the nth roots of unity. And so you get all the nth roots of unity are the nth roots are omega to the 0, omega to the 1, omega to the 2, omega to the 3, omega to the n minus 1. So omega to the 0 is 1, omega squared, omega cubed, omega to the n minus 1. Okay. And, since I'm assuming n is a power of 2, so in particular n is even, it turns out omega to the n over 2 is exactly minus 1, right? Because we know that omega to the n over 2 squared is just omega to the n, which is 1. So meaning omega to the n over 2 is either plus 1 or minus 1. In fact, it's minus 1 because these are all the nth roots of unity. Okay. So what that tells us is that if I give you the nth roots of unity, I can sort of, I can say, look, here are the nth roots of unity. Now let me figure out which are the n over 2th roots of unity. Well, which would be the n over 2th roots of unity? They'd be exactly the n over 2, which are an even power of omega. So the even powers are 1, omega squared, omega to the 4th, omega to the n minus 2 over 2, right? And then what are the square roots? Well, this would be 1 minus 1. This would be omega. Minus 1 is omega to the n over 2. So it would be omega to the n over 2 plus 1. Omega squared, omega to the 2 plus n over 2, etc. Okay. So anyway, we'll come back to these. So I just wanted to give you a big picture of which are the endpoints that we are going to be evaluating our polynomials at. They are going to be at these endpoints. These are the endpoints, the end roots of unity. Okay, so again, what's the FFT? We go from the coefficient representation A0, A1, A n minus 1 to the value of the polynomial at 1, omega squared, omega to the n minus 1, where omega is a primitive nth root of 1. Okay, meaning it's omega such that omega to the n is equal to 1, but no smaller power of omega equal to 1. Okay, so if you're looking at fourth roots of unity, it's like I, not -1 or 1, because a smaller power of -1 is equal to 1. Okay. And we can come back and look at properties of complex numbers to understand what the properties of omega are. But there are two basic properties that we are going to use. The first property is omega to the n over 2 is equal to -1, right? Because when you square it, you get 1, and omega to the n over 2 could not have been +1 because that's the smallest power of n that gives us 1. So that's what it means to be primitive, right? There's no smaller power of omega that gives us 1. And the second property that we have is omega squared is a primitive n over 2th root of 1. Right? Why is that? Because omega squared to the power of n over 2 is just omega to the n, which is 1. Right? Okay, so these are the two properties that we're going to use. Okay, so now let's see, how do we go from the coefficient representation to the value representation? So remember what I had said before. Well, the way you do it is you would take the coefficients a0, a1, an minus 1, and you'd multiply by the matrix, right? Remember what the matrix was? It consisted of, each row was 1 x squared, x to the n minus 1. So x is going to be, the first row is x is going to be 1, so you get 1, 1, 1, 1. For the second row, you'd get 1 omega squared, omega to the n minus 1. Third row, you'd get 1 omega squared, omega to the 4th, omega to the 2 times n minus 1. Third row is 1 omega cubed, omega to the 6th, omega to the 3 times n minus 1. Last row, 1 omega to the n minus 1, omega to the n minus 1 squared. Right? Okay, so if you look at this matrix, here's what it looks like. The jkth entry looks like omega to the jk. Right? The jth row corresponds to omega to the j, and the kth entry says omega to the jk. Right? So we want to take this, we want to multiply by this matrix, which has this special structure that the jkth entry is omega to the jk. Okay. All right, so let's now try to explore the structure of this matrix just a little bit. Okay. And what I want to do is do the following. So let's see. Remember, n was a power of 2. And we are looking at this matrix whose jkth entry is omega to the jk. All right. So now to understand this matrix and to understand how we are going to do divide and conquer on it, we are going to rearrange this matrix a little bit. Okay, so let me do an example. So let me think of an n equal to 8. So an 8 by 8 matrix. Okay, so J is going to go from all the way from 0, 1, 2, etc., all the way down to 7, right? So let me just write out 0, 1, 2, 3, 4, 5, 6, 7. So I want to cut it in the middle. Okay. And I want to think of this as 0, 1, 2, 3. And these I want to rewrite as 4 plus 0, 1, 2, 3. Okay. So I'm going to divide it into the first four rows and the next 4 rows. And the first 4 rows I'm going to index by 0, 1, 2, 3. And in the lower half, I'm going to say, well, these 4 rows are still rows number 0, 1, 2, 3, except they're in the lower half. And then the columns, I want to also renumber. So what I'm going to do is renumber these columns as being 0, 2, 4, 6. So I'll rearrange the columns. So I'll take all the even numbered columns and move them to the front. And all the odd numbered columns, I'll write here. 1, 3, 5, 7. Okay, is it clear? So I'm just taking the matrix and I'm rearranging it a little bit by rearranging the columns. And now, and rewriting the rows. And now I want to understand what each of these 4 submatrices look like. Okay. Okay, so let me write this down as Fourier transform sub n. So this matrix I want to think of as Fourier transform sub n. So what I'm going to claim is that this matrix, this submatrix is going to be Fourier transform sub n over 2. Okay. This matrix is also going to be Fourier transform sub n over 2. Okay. What do you think this matrix is going to be? Well, it's also going to be something like Fourier transform sub n over 2. Not quite, but something like. And what about this last one? What's this going to look like? Well, it's also going to look something like Fourier transform sub n over 2. Okay, this is going to set up our divide and conquer. Because in order to, we want to multiply Fourier transform sub n times this vector of, the coefficient vector. And in order to do this, we can express it as almost the problem of doing 2 smaller Fourier transform computations. Okay, so let's see why we can go from here to here. So here's how we are going to do it. So let's do our numbering that we promised. So we are going to go from. So we are going to look at a typical row here as j in the top half, but now j only goes from 0 to n over 2 minus 1, right? Only the top half. And then the corresponding row in the bottom half, we are going to number as n over 2 plus j, right? So the top half goes 0 to n over 2 minus 1. The bottom half goes, well, there's an offset of n over 2, and then it still goes 0 to n over 2 minus 1. For the columns, we are going to number them. The typical column here is going to be 2k. Again, k goes from 0 to n over 2 minus 1, so half the way. And then the corresponding column here is going to be 2k plus 1. So all the even ones are on the left half, all the odd ones are on the right half. So we just we rearrange the matrix. So now let's see what's this entry. It's omega to the 2jk. What's omega to the 2jk? Well, omega to the 2jk is just omega squared to the power of jk. Right? Remember, what's omega squared? So omega was the nth root of unity. It was a primitive nth root of 1. what's omega squared? It's the primitive n over 2th root of 1. So basically what we've done out here, if you just put your attention to this matrix, this submatrix, it's the Fourier transform matrix, but for n equal to n over 2, right? Okay, let's look at this value. So this is omega to the 2 times n over 2 plus j times k. So what's omega to the 2 times n over 2 plus j times k? Well, this is omega to the n times k plus 2jk, which is omega to the n times k times omega to the 2jk. But what's omega to the n times k? Well, remember, omega to the n is 1, so omega to the n to the k is just 1. So this is again omega to the 2jk, which is exactly like the top matrix. So we had concluded that this submatrix was just the Fourier transform matrix on n over 2. Same's true for the bottom half. It's just the Fourier transform matrix on n over 2. Right? Okay, so now let's look at this submatrix on the top right corner. Okay, so what's a typical element? What's this element? It's omega to the j times 2k plus 1. Okay, now this gives us a little more to work with. So let's see. Let me just cordon this off. Omega to the j times 2k plus 1. What's this equal to? Well, this is omega to the 2jk times omega to the j. Okay. So it's as though, with this omega to the 2jk, it's as though we had the Fourier transform matrix for n over 2, except that the jth row is going to be multiplied by omega to the j. So by abuse of notation, let me write this matrix as omega to the j times Fourier transform of ft of n over 2. So I'm saying omega to the j times ft n over 2. By abuse of notation, this is ft n over 2 with jth row multiplied by omega to the j for every j, right? You take every row and you multiply it by omega to the index of the row. And if you do the same thing for this the bottom right corner, you'll get almost the same thing. What you'll see is that the matrix is minus omega to the j ft n over 2, meaning it's the n over 2 by n over 2 Fourier transform matrix, except with the jth row multiplied by minus omega to the j. Okay. All right. So now let's see that. Okay, we have 10 minutes left. Let me just go through the divide and conquer algorithm. It'll take 5 minutes, and then we'll do questions. Okay. So let's see what we were trying to do. We wanted to compute ft sub n times this matrix times this vector a0, a1, a sub n minus 1. What we did was we said, suppose we rearrange the columns of the matrix, right, into evens and odds. So we sort the columns into evens and odds. Okay, so we rearrange the matrix into even, odd. Right? Now remember, when we sort the columns into evens and odds, we also have to sort the indices of this vector into evens and odds, right? Because we are going to take this this vector and we are going to multiply matrix times vector, we take this vector and lay it across like this. So we had better have the right, you know, the coefficients match up with the correct columns. So what we're going to do is sort these as A0, A2, A4, A1, A3, ... So evens and odds. And now what we said is, actually what happens is that here we get the n/2 Fourier transform. Here we get the n/2 Fourier transform. Here we get omega to the j times the n/2 Fourier transform. Here we get minus omega to the j times the n/2 by n/2 Fourier transform. Okay. So let me call this top half of the vector A sub even, and this A sub odd. Right? That's the top vector, that's the bottom vector. So now, what should the result be? So suppose we compute the n/2 Fourier transform of A sub even. And we also compute the n/2 Fourier transform of A sub odd. Okay. Can we use these to piece together what the Fourier transform of this larger vector is? Well, the answer is yes. We can easily piece those together because look, what's this top half going to look like? What's, you know, so if we let me make it a really fat vector over here because I'm going to have to write a lot. So what's the top half going to look like of this vector? Well, you see, we are going to take A sub even and multiply it by ft(n/2). So we'd get the Fourier transform of A sub even plus we're also going to take the Fourier transform of A odd. Oops, I knew I had to make it fatter, so let me just make it really fat. So ft(n/2) times A odd, except that the jth row I'm going to have to multiply by omega to the j. But that's easy, right? Once I've computed this, I can just multiply the jth entry by omega to the j, right? How much time does it take me? Well, it takes me a linear amount of time, one multiplication for each entry and then one addition for each entry. What about the bottom? Well, it'll be again ft(n/2) A even minus omega to the j ft(n/2) A odd. Okay, so what did I have to do in order to do this? Well, I just had to do these two multiplications. And then I just copy those values down here, right? There are n/2 values, I copy them down here. And I copy the same values down here. I take these values, I copy them down over here, multiply the jth one by omega to the j, and add to the corresponding entry over here. Multiply the jth one by minus omega to the j, add the value to the corresponding entry here. So how much time did I take? Well, t of n equal to 2 times t of n/2, right? Those are these two, plus big O of n, right? Because there were n entries, you know, I copied down these n entries twice, or n/2 entries twice, multiplied the jth one by omega to the j, added, so that was order n operations altogether. And so again, you know, master theorem, or, you know, you can do it by hand. Explicitly, t of n is order n log n. Okay. So that's the basic algorithm. Now, there's a lot more to think about it. We'll do it again in the next lecture, but I hope that this was sufficient for you to see, you know, in a big picture, what the FFT algorithm is, and to understand how it works, and, you know, where does it get its speed up from, You know, what's the main structure? Okay, so I'll stop for questions.
Can we circle back first to the even odd split up of the polynomials? I think that would be a good point to clarify based on the chat.
Even odd. Okay, so suppose that our polynomial was 1 plus 5x plus 2x squared plus 3x cubed. Okay, so how would you write it? You'd write it as 1, 5, 2, 3. Okay, so now we do a rearrangement. So after we rearrange, what we would do is take the even numbered coefficients. So this is x to the 0, x to the 2. We'd move them to the top. So we'd have 1, 2. And then we take the odd numbered coefficients, which are this, and move them to the bottom, 5 and 3. Okay. And the reason it's okay to do this is because we've taken the columns of the matrix, and we've taken the even numbered columns and moved them to the front, and the odd numbered columns and moved them to the end. So because we did the same thing to the matrix as we did to the vector, the results are going to be the same. Okay.
I think some people are interested in the inverse FFT and how it's related to the matrices and the matrix representation of FFT.
Yeah, that's a very good question, and we'll get there next time. So it's you know, so I'll describe it to you in several ways. You know, there's a mechanical way to describe it, and then there's, you know, then there's the bigger picture way of describing it. I'll describe both to you, and you know, depending upon the level of sophistication you like, you can follow it at that level.
Oh, there are hands raised. Thank you, the person who told me this. Kentaro and Pavana and Saad. I may be mispronouncing names, and I'm sorry if I am. How about first Kentaro, because he's on the top of the list, which I think means he clicked it first.
I was a little confused by the nth roots of 1. So can you go back to where you drew the tree and you got the 4th root of 1? So could you circle where on the tree the 4th root is?
What are these are the 4th roots of 1. 1, minus 1, I, and minus I. And
So
of these two are both primitive roots, I and minus I. So if you start from any of them and you take all the powers, you know, if you raise it to power 0, 1, 2, 3, you'll get all the 4th roots of unity. So that's what I illustrated down here. You can, you know, you can look at the, you can start with I or minus I, and then you raise it to power 0, 1, 2, 3, or here I did 1, 2, 3, 4, and I got all the 4th roots of unity. Okay, so these are the primitive 4th roots of unity. And so when we do the fast Fourier transform, we'd start with one of these. So let's say we'd start with I. So this would be omega, and then we'd evaluate at 1 omega, you know, 1 omega, omega squared, etc. But this would be omega.
Okay. And then other primitive roots of unity, or are those just the ones we're going to use for this class?
Well, no. So they are going to be, you know, okay. So again, I'll do this in greater detail next time. But there's a way to picture the complex numbers. What you do is you draw the number line. So this is the real, and then, you know, so here you have 0. There's 1. There's minus 1. And then the imaginary numbers we think of as orthogonal, you know, they're completely unrelated to the real numbers. So we draw them perpendicular. So that's the imaginary axis. And here's I, and here's minus I. Okay. And if you look at all the roots of unity, they lie on this unit circle. Right? And basically, the way it works is, you know, the nth roots of unity sort of are equally spaced on this circle. So this is omega to the 0, and you know, if you let omega be, you know, so this would be 2 pi divided by n. So that would be one of the primitive roots of unity. So that might be omega to the 1. And then you keep spacing these out equally as you go across the circle, right? And this would be equal to also omega to the n, right? So omega to the 0 is omega to the n is 1. And then you know, if you remember your complex multiplication, okay, we'll do this more slowly next time, but if you remember you know, if you multiply this number by itself many times, then the magnitude sort of gets powered up. So in this case, the magnitude is 1, that's this radius. So it stays on the unit circle. But this angle, you know, when you square this number, the angle doubles. When you cube it, the angle triples and so on. So if you multiply it by itself k times, the angle increases by a factor of k. So in order for that the number comes back to here, you know, when you multiply by n, when you multiply the angle by n, it has to be either 2 pi over n or one of its multiples. So these are all the nth roots of unity. There are exactly n of them, and they you know, they're equally spaced on the unit circle. And so we'll usually choose this one to be the primitive nth root of unity, e to the power, you know, this is the one that makes this angle of 2 pi over n. So it's essentially cosine 2 pi over n plus I sine 2 pi over n. So that's omega, the nth root of unity, and then its powers are the other roots of unity. Okay.
I think I just need to review complex numbers.
I'm sorry?
I think I just need to review complex numbers. Totally forgot this.
Oh yeah.
There's a great review on page 74 of the textbook, which you can find in the chapter 2 link. It has the whole picture and multiple representations drawn out really nicely, in case anyone needs another resource.
All right, thank you.
Do we have time for Bhavna's question?
Yeah, actually, you know, we have plenty of time because, you know, my office hours go till 5:30, so I'm going to stay till 5:30, and you're welcome to stay as long as you want and ask questions, so we can keep going.
Okay, so my question was, you know, on the next slide, when you multiply ft and over 2 times a even.
Right here, or last slide here?
Last slide, yeah.
Yeah.
I was wondering, does that not count as part of the O of n time because it's returned as part of the recursive call?
This, you know, when you compute this is your recursive call, right?
Okay, so the whole algorithm is for calculating ft times a, not for calculating ft.
Right. So ft itself is this matrix, right? So what's the Fourier transform, right? So it takes a naught, you know, it takes this coefficient representation. Now, the fast Fourier transform is an algorithm that converts this into a of 1, a of omega, a of omega to the n minus 1.
Okay.
Right? And so that turns out to be multiplying the coefficient vector by this Fourier transform matrix.
Okay, that makes sense.
Yeah.
Okay, we might have another question from Saad.
Yes, hi, Professor. Could you go back to that slide where you showed the Fourier transform matrix? I think it's, yes, this one. That omega is the primitive nth root, right? Could you explain where the, you said that the j comma kth entry of the matrix will be omega to the jk.
Right.
How did you get that?
Okay, so So when you look at the jth row of the matrix, it would be 1 omega to the j, omega to the 2j, omega to the n minus 1 times j, right?
Yes.
Because the 0th row, first row, second row, third row, jth row. Now, if you're going to look at the kth entry, so the 0th entry is omega to the j times 0. The first entry is omega to the j times 1. Second entry is omega to the j times 2. So the kth entry is omega to the j times k. Right? That's
Okay.
what I wrote here.
And then since there can be multiple primitive nth roots of unity, does it matter which omega you use?
It doesn't much matter. So one way you can write the algorithm is you say, this is the FFT with the following value of omega, right? You can choose any primitive nth root of unity. By convention, we'll always use, we'll just use omega equal to, this e to the 2 pi I over n, right? So the one that I showed you, it's the cosine 2 pi over n plus I sine 2 pi over n. But it's not necessary. You can use any primitive nth root of unity, right?
Mm-hmm. Okay, and then just really quick, if that's okay. In the unit circle diagram, if we were to take all the nth roots of unity and square them, does that correspond to taking an evenly, for example, let's say it's the 8th root, 8 evenly spaced points around the circumference, and then making them 4 evenly spaced points around the circumference?
Exactly. Yes.
Okay, thank you, Professor.
Okay,
So-
we also
so in-
have, oh, sorry.
Yeah. So in fact, when you do that, 8 will become 4, and the way that will happen is for every one of those 4, there'll be 2 of those 8th roots which will map to it. It's just like when you square 1 and minus 1 both collide in 1, right? 1 squared is the same as minus 1 squared. So what you'll be able to do is pair up these roots. So you have omega, and then you have minus omega over here. And both of these, when you square them, will give you omega squared. So the reason is when you square this one, you'll get this, because you'll get from 2 pi over n, you'll get to pi over n. Here, you'll go from pi over 2 plus pi over n, 2 pi over n. When you double that, this pi over 2 doubles to get 2 pi. 2 pi is the same as 0. You've gone all the way around, right? And then there's this little bit. This little bit is the same as that little bit. So when you double this angle, you go all the way around and then this much. So this and this point, when you square them, you end up, both of them end up at this point, right? So that's what happens when you square.
Okay, we also have Animesh and Kentaro again. If people want to ask more questions.
I believe Kentaro was first, so he should go.
Oh, okay. Thank you. Wait, could you explain again how you squaring it flattens it so that it ends up in the same place?
Okay, so look, here are 2 points. This is omega. This one is minus omega. Okay, so to go from a number to minus of that number, you reflect, you take it, you go through the origin and you extend out this way. Now when you square these two, when you square this one, the angle doubles, right? So you get to this one. When you square this one, the angle doubles. But what's the angle? It was all of this, right? So this is pi plus this much. This much is the same as 2 pi over n. So it's pi plus 2 pi over n. Now when you double that, this pi doubles to give you 2 pi. 2 pi is the same as 0, right? If you go all the way around the circle, you come back to where you started. Then if you take pi plus 2 pi over n and you double it, well, you go all the way around, and then you still go twice of 2 pi over n. But twice of 2 pi over n exactly brings you here. Right? So you end up back in, in the same. Okay.
And then when you square the positive w omega, why does that double the angle?
Anytime you square a complex number, the angle gets doubled.
Oh, okay.
Right?
Hi, Professor. I wanted to very quickly touch on the notation that you used on the last slide. So I remember us earlier discussing that if you have omega to the power of j, the negative of that value would be omega to the power of j plus n over 2.
Yes.
And in that sense, when you've got those complex roots of unity, and actually I think I'm talking about the very last page of notes that you took before class ended, I noticed that we took the time to sort a sub 0 all the way through a sub 7 into evens and odds. I was wondering why this process was necessary, because wouldn't a sub 0 through a sub 3 automatically be the positive values, and then a sub 4 through a sub 7 would be the negative ones, using the process we discussed for like the negation of complex roots of unity?
Well, see, remember, we don't just have particular complex roots of unity. So we are looking at the entries of this matrix, and the jkth entry is of the form omega to the jk. And we want to understand the symmetries of this, right? And it turns out that the way to understand them is by actually, so we want to take this matrix and want to divide it into 4 pieces so that each of the 4 pieces looks almost the same. And it turns out the right way to do it is to divide it into evens and odds, and along one side. So we choose to do it along the columns. It's arbitrary, and then just into top half and bottom half along the rows. And then when we work out what the entries are now, what each entry looks like, they now look like the corresponding entries for the matrix half the size, n over 2 by n over 2. And so that's your symmetry. That's how we get the divide and conquer going.
Okay, I see now. Thank you.
Yeah, sure.
Well, I don't have any more messages in the chat right now. Oh wait, Kentaro might have another question.
Yeah, sorry. No one else has a question. I'm just gonna ask another one. But so why do we want to collapse the 8 values onto 4 in the first place? Like, what was our motivation for that?
What was the motivation? Look, okay, so let's go back to the beginning, right? What were we trying to do here? Remember, we were trying to go from this coefficient representation, right? This coefficient representation to the value representation at endpoints. Now, if we were going to do these endpoints one by one, it would take way too long, because each of these points, to compute the polynomial at each of these, if we are doing this individually, takes n steps. So the only way to speed it up is to choose related points in such a way that we can share computation between many of these calculations, right? So we want these calculations to overlap with each other as much as possible. And the way we choose to do this is we choose to do this so that maybe when we do the calculations for the top half, it's almost the same as the calculations for the bottom half, right? And so we want to take this computation and break it up into two pieces, right? Such that each of them is more or less the same, but it involves much smaller, so instead of doing the Fourier transform on n values, we do it on n over 2. And we have two such problems. So that's what we were aiming for. And so that's why what we're doing is we're saying, well, look, this is an n by n matrix. It looks very scary. But now, lo and behold, you rearrange it a little bit, evens, odds. And now you start looking at it, and it doesn't look so scary anymore in the sense that, it has 4 pieces to it, but all 4 pieces look more or less the same, right? So in fact, this large matrix, it could have been anything, but now we can say, well, it looks like almost the same thing. There are 4 small matrices, n over 2 by n over 2, and they're almost all the same matrix. With small variations, where some of these, the jth row is multiplied by omega to the j, but that's small potatoes, right? We can always, after we do the computation, we can just multiply the jth entry by omega to the j. So that's easy enough. So that's where we ended up. We had almost the same matrix 4 times. So we go ahead and divide our vector into 2, evens and odds, so rearrange, that's no sweat, right? So, and then we go ahead and now all we have to do is multiply the top half by this half size matrix, bottom half by the half size matrix. That's something that, well, that's divide and conquer at its best, right? So two subproblems of size n over 2, what could be better than that, right? And then the total amount of work it takes to glue these solutions together, well, okay, so all we have to do is add the corresponding vectors. So adding vectors, that's easy, right? Because you add component-wise. That's linear time. Multiplying the jth component by omega to the j, that's easy, right? That's constant times per entry, so linear time again. So all of this is linear time, the gluing. So now we have our, the recurrence that we really love, because it's same as sorting. T of n is 2t of n over 2 plus order n. That's n log n.
So are we just having to use omega because, like, in the beginning we realized like a of 1 and a of negative 1, we can like move it into this really like nice form, and then if we use the like roots of 1, then we can do that for like everything. So we just happen to like find that the roots of unity just happen to be this like really useful form. So we just like,
yeah, absolutely. So you can now see reverse engineer the whole process, and you can say, look, what was going on in here was this observation we had in the beginning that if you want to compute a of x and a of minus x, they're almost the same, because on the even terms they are the same, because if on all the even powers of x, minus x and plus x will give you the same thing. So the even polynomial is going to be the same. On the odd terms, with plus x you'll add, with minus x you'll subtract. So that's okay. Well, we can, if you just compute the even powers and the odd powers separately, then in the one case we have to add the 2 values, in the other case we have to subtract the 2 values. But that's okay. That so we got 2 different, the value of the polynomial at 2 different points for the cost of 1, with a little bit of extra addition or something. But essentially we got 2 for the price of 1. And if you can keep doing this recursively, then we get essentially n log n, because by keeping on pairing up, that's log n stages. So that's the amount of work we are doing.
So then I was also gonna ask, so in the beginning we were motivated by like the a of 1 and a of negative 1, we can represent it, and then we kind of like expanded on it, right? So then in this example, like where would a1 and a of negative 1 be? Like, would the negative ones just be like the odd ones, and the 1 would be like the even ones?
So when I did the example A of 1 and A of -1, you know, it was sort of a throwaway example. You know, what I was planning to do next time is I was planning to come back and talk about exactly what you were asking about, where I was going to say, well, instead of 1 and -1, if we were just evaluating the polynomial at x and minus x, even then, those two evaluations you can do essentially in as much time as one evaluation. Right? And so you get 2 for the price of 1 if you have x and minus x. And now if you want things of the form x and minus x, you know, as you go through the algorithm, then you're sort of forced into the nth roots of unity, because they have this property that these roots come in pairs, you know, x and minus x. And then when you square it, again, they come in pairs. And you square it, it again comes in pairs. So, you know, from the nth roots of unity, you go to the n over 2th roots of unity. But at any level, you know, if you have the 8th roots of unity, there are 4 pairs of them, right? There are 4 pairs of the form plus minus x, plus minus y, plus minus z, you know. Now you square them, you get the 4th roots of unity. They also come in pairs, plus minus 1, plus minus I. You square them, you get the 2nd roots of unity. They also come in pairs, plus minus 1. And then you square them, you get to 1. You know, so that's how your tree goes. So you have n nth roots of unity, all arranged in pairs, plus and minus. You square them, you still get n over 2, but they're all arranged in plus, minus, and so on. And so that's the clever choice of the endpoints that this represents.
So the property of like having like a minus, like having a dual, like having a counterpart, comes from the roots of 1. So it doesn't matter if like our like the b that we're applying, even if it's like all positive integers, because we have like the flipping thing, there's going to be like negative and positive applied.
Yeah, it comes from the fact that n is even, right? So when you look at the nth roots of 1, as long as n is even, then the roots will pair up.
Oh, okay. So that's why we do the n many roots. Oh, okay.
Yeah.
Okay.
Yeah.
That's
Okay.
what has to be even. Okay. Thank you.
Hi, Professor. Just had a question about what the kind of data representation of the complex numbers in the Fourier transform matrix would be. And is there like some runtime or like some overhead for actually computing these roots of unity? Or are we kind of
that's
just
a very good
way?
question. So yeah, you know, that's the whole great part about algorithms, is that you choose your level of abstraction. So for now, we're choosing our level of abstraction and saying, somebody handle complex numbers first, right? You know, our computer has them built in, multiplying them, adding them, it's all taken care of for us. And these numbers are not too large, so we don't even worry about how long it takes to multiply and add them. From our viewpoint, it's a unit step. Now, later you might say, but I'm not satisfied with that, because, you know, eventually I really have to keep track of these complex numbers. And what about precision issues and the fact that, you know, when you multiply complex numbers, you won't get the exact answer. So once you start thinking like that, then you get, you know, you get assigned a homework question which says, you know, you can actually do all this using modular arithmetic, and then it's finite precision, and you can keep track of everything precisely. And so once you work through that homework question, you'll understand, you know, you'll see that this abstraction wasn't really necessary. If you wanted to, you can get rid of this as well. Right? And I don't remember if it's a homework question on this homework or the next one, but
I think it's this one, unless they removed it. I'm not positive.
Okay, good. Good.
Yeah, a bunch of questions about the roots of unity came up in the chat, and I tried to mention the modular arithmetic thing as an analogy, but I may have overcomplicated it. I don't know.
Oh, thanks for doing that. Yeah, no, that's good.
Does anyone else want to jump in? Oh.
What was the analogy with the modular arithmetic? I didn't see the chat.
You know, you'll work through that for a homework problem, and I'm sure there might be something about it in discussion as well. But essentially, essentially there are only two properties of omega that we needed. One, that the powers of omega are all the nth roots of unity, and then the even powers are the n over 2th roots of unity. And then, you know, they come in pairs, plus and minus. And so if we can achieve that same, those properties with you know, in modular arithmetic, then we don't have to use complex numbers. You know, the complex numbers came up just because we wanted those roots of unity. So if we can get those using modular arithmetic, that's just as good for us.
Okay.
Right? Yeah.
Hi, Professor. In 70, we learned about this interpolation process, but we did it through Lagrange interpolation. I
Yes.
was wondering, do we use like the inverse of FFT here because it's significantly faster? Or is there some other reason we use it? Okay.
No, you're right. So the reason we use the inverse FFT is because it's significantly faster. So remember, you know, even in terms of moving from the coefficient to the value representation, we could do it, you know, we could do it using the pedestrian method, and that would take us n² steps. If we were to do interpolation using Lagrange multipliers, it might even take us more than n² steps, right? So that's not going to be a good thing for us. So the point is, in moving from the coefficient to the value representation, we use the special points that we were evaluating at, right? So we had a special choice of points that we used. So also to do the interpolation, we are going to make use of that special choice of points. And in fact, it turns out the inverse Fourier transform is going to look almost exactly like the Fourier transform algorithm. So we won't even have to redo the algorithm. We'll just have to make an observation and understand what the Fourier transform looks like. And therefore, we'll understand what the inverse Fourier transform looks like. And it'll be the same algorithm, essentially. So that's how it's going to work out.
Thank you.
How did the moderating style go?
Oh, that was great. You're natural.
Thank goodness. Did you see any of the questions in the chat throughout the lecture?
You know, I was relying on you. So
okay.
You know, you exuded confidence, so I didn't even look.
Okay, because yeah, there were a lot. I think that they were mostly answered. But when I was interrupting you, like when you were about to ask for questions, and I mentioned what the topic was, it was mainly from the chat questions. But yeah, I was just curious if you had seen them and you thought I should be answering, saying fewer things.
That was fabulous. Thank you very much. Yeah, that was great.
No problem. I actually really enjoyed this, so I love this job. But also it's because I really love FFT, so I don't know if I know every topic as well. So also there's Nima, another tutor or reader. Wait, Nima, are you a tutor?
Tutor, yeah.
He was also helping me answer the questions because apparently he's going to be doing it in future weeks. And he covered a lot of the signal processing questions at the beginning because I don't know as much about that application of FFT.
Yeah, I think in the beginning there were a lot of questions in that side who were confused. People were confused about LTI systems and like how, I guess, like convolution worked and how like the impulse response corresponded to the system. So yeah, I was trying to resolve that, but we went past it. So I think it was resolved.
Well,
Yeah.
Thanks a lot. That's really helpful. Actually, now that you mention it, I should have. I was trying not to introduce terminology, but possibly if I'd said convolution multiplication, it might have, you know, it might have evoke the right response for some of the students at least. So,
yeah, totally. I'm not sure. I'm just a tutor that just joined, but we could possibly make a Piazza post if people have questions regarding like the initial part where there was a lot of signal processing.
Yeah.
Or do you rather we don't do that because like that's not the main point?
Oh well, you know, if you see any questions, please do. You know, if you see that people still are, you know, have questions about it, then do please make a post.
Yeah, I think we should make a post explaining the signal processing problem setup and how it uses FFT as a black box, because as soon as we jumped into the FFT theory, there were a lot of questions came up about how A and B were being transformed and then multiplied and then sent back.
Yeah, sounds great. Yeah.
If I remember correctly, one of our TAs, Nate Young, he wrote some exposition about that, like maybe last year or something. So probably we can share it with everyone as well.
Yeah, actually, it would be great if one keeps a running, you know, takes whatever one has inherited and then edits it further, and you know, so you can incorporate more into it or less into it, you know, make it shorter or longer as you feel appropriate.
One of the questions that you were asked, I was thinking about, like, is it possible to do general interpolation in n-log n time or close to it, or is it simply impossible?
It has to be hard, right?
I don't remember. I mean, it seems vaguely like
I think
I heard sometime, but I couldn't find it on Google.
I think that just the fact that you know, that's sort of like if you want to invert the van der Monte, you know, that's one way to do it. But there, the fastest is n squared. General interpolation.
Oh, can I ask a question?
Yes.
Yeah, I was gonna say a post about like the convolution multiplication would be really good, because I didn't really understand the whole LTI thing either. But yeah, that would be really good. But is there like a section in the text that has more about the LTI?
There is a in the FFT section. There's a how do you call it? There's a box about LTI. You know, so it's just a page or so, and so possibly a Piazza post that elaborates on it might be something that you know. So you could try reading that box. That's a page, and so we try to condense the essential features there, but you know, but sometimes longer exposition might help. So in that sense.
Yeah, thank you. That'd be really good.
Yeah.
I should probably stop the recording. I don't know if it's possible to trim it later. I just hope that there was. Do you think there's anything else we should record?
I think this should be a good time to stop. And,
we already
yeah.
have like 2 hours, so.
Yes.
Okay.
Great.
Stop.
I was